compact conductor table, such as Table CANIA in the National Electrical Code, provides data on compact conductors. These conductors are designed to reduce the overall size of electrical systems by incorporating multiple conductors into a single space-saving design. The compact conductor table is separate from the standard conductor table, such as Table CONE, for several reasons. Firstly, there are different characteristics. Compact conductors have a smaller diameter than traditional conductors for the same current carrying capacity. They are designed to be installed closer together, which reduces space requirements. Furthermore, the ampacity of compact conductors may differ from traditional conductors because of their different construction and cooling characteristics. Secondly, there are special considerations for compact conductors. Their installation requires specialized techniques and tools to ensure proper connections and to avoid damage. The current distribution within a compact conductor can be different from that of a traditional conductor, which affects heat dissipation and temperature rise. Compact conductors can generate a different magnetic field pattern than traditional conductors, a factor that may be important in certain applications. Thirdly, there is codification. The National Electrical Code classifies compact conductors as a distinct type of conductor, separate from traditional conductors. A separate table for compact conductors ensures that the data and requirements specific to their use are clearly differentiated from those of traditional conductors. By having a dedicated compact conductor table, the National Electrical Code provides clear guidance on the installation and use of compact conductors, accurate data on their electrical characteristics, including ampacity and resistance, and safety requirements and limitations specific to compact conductors. Ampacity is the current carrying capacity of a conductor, typically measured in amps. It's the maximum amount of electrical current a conductor can carry continuously without exceeding its temperature rating. Several factors affect ampacity, including the conductor size, material, insulation type, and the surrounding ambient temperature. The National Electrical Code, or NEC, provides tables that specify the allowable ampacities for various conductors under different conditions. These tables are essential for ensuring electrical systems are designed and installed safely. Resistance is the opposition to the flow of electric current in the conductor, measured in ohms. All conductors have some degree of resistance, which converts electrical energy into heat. The amount of resistance depends on the material, length, and cross-sectional area of the conductor. Longer and thinner conductors have higher resistance, while shorter and thicker conductors have lower resistance. Understanding conductor resistance is important for calculating voltage drop and power loss in electrical circuits. Voltage drop is the decrease in voltage along a conductor due to its resistance measured in volts. As current flows through a conductor, some of the electrical energy is lost as heat due to the conductor's resistance, resulting in a voltage drop. Excessive voltage drop can cause electrical equipment to malfunction or operate inefficiently. The National Electrical Code sets limits on the allowable voltage drop in branch circuits and feeders to ensure proper operation of electrical equipment. Proper conductor sizing is critical to minimize voltage drop. National Electrical Code Section 210.19.81 states that branch circuit conductors shall have an ampacity not less than the maximum load to be served. Conductors must be sized to carry the intended load without overheating, considering factors such as ambient temperature and the number of conductors in a raceway. Section 310.15 provides guidance on determining the allowable ampacity of conductors. Overcurrent protection devices, such as circuit breakers and fuses, protect conductors from overloads and short circuits. These devices are designed to interrupt the flow of current when it exceeds the conductor's ampacity, preventing overheating and potential fire hazards. The National Electrical Code requires that overcurrent protection devices be selected and installed in accordance with the conductor's ampacity and other relevant factors. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and clear the fault. Bonding connects non-current carrying metal parts together to create an electrically safe path, minimizing the risk of electric shock. The National Electrical Code contains detailed requirements for grounding and bonding electrical systems. Section 250 covers grounding and bonding requirements. Wiring methods refer to the different ways electrical conductors can be installed and protected. Common wiring methods include conduit, cable, and direct burial. Each wiring method has its own advantages and disadvantages, and the selection depends on the specific application and environmental conditions. The National Electrical Code specifies the requirements for each wiring method, including conductor support, protection, and spacing. Conduit is a rigid or flexible metal or plastic tube used to protect electrical conductors. Conduit provides physical protection for conductors and can be used in a variety of environments, including wet, dry, and corrosive locations. The National Electrical Code specifies the types of conduit that are permitted for different applications. Cable consists of two or more insulated conductors enclosed in a protective sheath. Common types of cable include non-metallic sheath cable, armored cable, and metal-clad cable. Cable is commonly used in residential and commercial wiring for branch circuits and feeders. The National Electrical Code specifies the types of cable that are permitted for different applications. Direct burial is a wiring method in which conductors are buried directly in the earth. Direct burial cable is specifically designed for this purpose and is resistant to moisture, corrosion, and physical damage. The National Electrical Code specifies the requirements for direct burial installations, including burial depth and protection from physical damage. Terminations and splices are the points where conductors are connected to equipment or to each other. Proper terminations and splices are essential for ensuring reliable electrical connections and preventing overheating and arcing. The National Electrical Code specifies the requirements for terminations and splices, including the use of approved connectors and methods. Electrical boxes are enclosures used to house electrical connections such as switches, receptacles, and splices. Electrical boxes provide protection for the connections and prevent accidental contact with live parts. The National Electrical Code specifies the types of electrical boxes that are permitted for different applications and the requirements for their installation. Raceway fill refers to the amount of space occupied by conductors in a raceway, such as conduit or tubing. The National Electrical Code limits the amount of raceway fill to ensure adequate ventilation and prevent overheating of conductors. The allowable raceway fill depends on the type of raceway, the number of conductors, and the size of the conductors. Voltage drop calculations are used to determine the voltage drop along a conductor due to its resistance. These calculations are important for ensuring that electrical equipment receives adequate voltage and operates properly. The National Electrical Code provides guidelines for calculating voltage drop in branch circuits and feeders. Short circuit current calculations are used to determine the amount of current that will flow during a short circuit. These calculations are important for selecting overcurrent protection devices that can safely interrupt the fault current and prevent equipment damage and fire hazards. The National Electrical Code provides guidelines for calculating short-circuit currents in electrical systems. Ground fault protection is a system designed to detect and interrupt ground faults, which are unintentional electrical connections between a live conductor and ground. Ground fault protection is required in certain applications to protect people from electric shock and to prevent equipment damage. The National Electrical Code specifies the requirements for ground fault protection in various types of electrical systems. The use of appropriate tools and equipment is essential for safe and effective electrical work. This includes insulated tools, voltage testers, and personal protective equipment such as gloves and safety glasses. The National Electrical Code requires that electrical work be performed by qualified persons who are trained and knowledgeable in the safe practices and procedures. Electrical safety is paramount when working with electrical systems. Always to energize circuits before working on them and follow lockout-tagout procedures to prevent accidental energization. Be aware of potential hazards such as exposed conductors and energized equipment, and take precautions to avoid electric shock and other injuries. Always follow the National Electrical Code and other applicable safety standards to ensure a safe working environment. When considering the compact conductor table versus the standard conductor table, remember that compact conductors offer space-saving advantages due to their reduced diameter. However, They may require specialized installation techniques and tools. Always consult the National Electrical Code to ensure compliance with all applicable requirements and to ensure the safe and effective installation of electrical systems. This is extremely important for any electrical project. Remember to always consult with qualified electricians or electrical engineers for specific project needs.